Hello, my name is Liang Zhao. I'm from the Center for Autonomous Systems at the University of Technology, Sydney. Today, I'm going to talk about our work on FeatureBased SLAM, why simultaneous localization and mapping. At the beginning, let me show you some interesting results in the FeatureBased SLAM. When we use Gauss-Newton to solve nonlinear least square formulation of FeatureBased SLAM, at the beginning of each iteration, we set feature locations at random values. But after each iteration, the SLAM result is exactly the same as it's solved normally after each Gauss-Newton iteration. In this paper, we mainly proved two theorems in feature-based SLAM problems. The first theorem is when the covariance matrix of feature observation errors are isotropic, the robot poses and feature positions obtained in each Gauss-Newton iteration are independent of the feature positions in the previous step. The theorem is based on the assumption that the covariance matrices of feature measurements are isotropic. Then we can formulate the feature-based SLAM as the nonlinear least square problems. A traditional way is to use Gauss-Newton to solve the optimization. To prove the theorem, here we use true complement, which first solve the update of reduced robot system, and then perform back substitution to get the feature update. Here we also give a very important lemma that the observation function is linear in features, and given the data association, the Jacobian with respect to the features is constant. Then, based on lemma 1, we can prove that the update of robot pose is independent of features. We can also prove that although the update of features is dependent of features, the features after the update is independent of features. Thus, we proved the theorem 1. Based on theorem 1, an equivalent pose-only algorithm is proposed, which means only robot poses need to be solved in the feature-based SLAM, but it is equivalent to solving the complete SLAM problems. We also use Victoria Park and DOR datasets to validate the proposed pose-only algorithm. We can see from the results that the robot poses obtained from the pose-only algorithm are exactly the same as those obtained from normal Gauss-Newton method in each iteration. We also validate our findings in the 3D scenario using simulation by both setting random feature values and perform pose-only algorithm. And we can see the results are the same as those obtained from full nonlinear least square SLAM. Then we further prove the second theorem that when the covariance matrices of the odometry translation errors are also isotropic, the SLAM results are independent of both feature positions and robot positions. The proof of theorem 2 is similar to the proof of theorem 1, and we can also have an equivalent rotation-only algorithm, which only solves rotations, and it is equivalent to solving the full feature-based SLAM problem. Again, we first validated by setting feature and robot locations as random values at the beginning of each iteration. As we can see from each iteration, the updated robot poses and features are exactly the same as those from the normal Gauss-Newton iteration. Then we also perform the proposed rotation-only algorithm, and we can see the results are the same as solving the complete SLAM problem. For more information, please refer to the paper. Thank you very much for your attention.